everyone. Good afternoon. Welcome to the Structure Tech Building Envelope Restoration webinar. Thank you so much for joining us this afternoon. I'm Nick O'Hare, and I'm a Client Relationship Manager with Structure Tech.
And I'm Russ Thurston. I'm the Restoration Division Manager.
And again, we really just thank everyone so much for taking the time out of their day this afternoon to join us. And Russ and I were talking just before we joined on here, and it's really just amazing to us. Every time that we do these webinars, it's so neat to see really the reach that we can have with these, and really no other venue could allow for attendance like this. We have attendees from Texas, California, Georgia, New York, Illinois, Michigan, Florida, really every region of the country. Even we have a couple of attendees north of the border in Canada. Every region of the country is really tied in today, and also attendees from manufacturing, corporate sector, environment, healthcare, school districts, just very, very well represented, and I think that's amazing. So today we're going to be covering building envelope restoration, and typically when Russ will do this seminar, it's a 4-hour presentation that he gives, so we really had to go through here, cut a lot of things down, really into 55 minutes, focusing on the most common types of wall systems that we find in the market today, the most common components within each wall system, and really ending on identifying and solving problems with these wall systems. So the format today is going to be about 55 minutes of presentation, and we're going to leave 5 to 10 minutes at the end for question and answer. And how the format for the question and answer is going to work, you'll notice that there is a box here on your screen where you'll be able to enter a question at any time. Feel free to enter that. But for time's sake, Russ and I are going to wait to the end to answer those questions. So we'll get to as many of your questions as possible. And if we're unable to get to any question, we will make sure to follow up to make sure that's answered. So if you've ever been to a Structure Tech seminar or symposium or seen us at a trade show, specifically one of my presentations, there's always a couple takeaways and a couple comments that people say. And one, typically, and I hope this is always the case, that there's some really good takeaways that we got out of the presentation. And this is really something that we could implement when managing our facilities, and just some really, really good takeaways, good information. Two is, Nick, you sure do tell some lame jokes, and you find some pretty comical ways to get some of this across. So I think I need to stick with that. So a joke that I find that really relates to our topic today well is you have to know what you're getting yourself into. So there's a story of a burglar. A burglar was casing this neighborhood, in a great neighborhood. He saw this family was going on vacation. He finds out when they're going on vacation, so he shows up when they're gone, gains entry to the home, and he sees, oh my goodness, there is a big screen TV in here, and I really want that. He goes over to the big screen TV, starts unplugging all the cords, gets this thing ready, and all of a sudden he hears a voice, and this voice says, Jesus is watching you. So he freaks out, and he takes his flashlight, starts looking around the room, doesn't see anything, and he attributes it to his conscience. Completes the TV, and then he sees the stereo system. He goes over to the stereo system, starts unplugging the cords. Again, he hears Jesus is watching you. Looks around, doesn't see anything. Finally, he gets everything unplugged. He's got it in his hands. He's walking out to the truck. One last time, he hears, Jesus is watching you. He says, okay, that's it. I'm going to get to the bottom of this. Takes his flashlight, searches the room. Finally, he sees a bird cage in the corner. He walks over to this parrot's cage, and he says, hey, parrot, was that you? No response. Finally, he shines his light on the parrot's name tag, and the name tag of this parrot is Moses. And he says, well, what kind of family would name their parrot Moses? Finally, the bird responds, well, the same kind of family that would name their Rottweiler Jesus. So obviously this burglar did not know what he was getting himself into. And this relates very, very well to this presentation today because building envelope technology is so very, very complicated. And at the end of the day, Russ and I want to make sure that we give you the information that you need so next time you're casing your building, you're engaging in a project, you know exactly what you're getting yourself into. So without further ado, let's move on. First, what is a building envelope? A building envelope is all of the components that keep the exterior elements, specifically water, moisture, from entering the interior of the building. It really includes all of the components shown within this depiction here, this graphic. It includes your roofing system. It includes your wall systems. It includes your window systems. It includes all of the flashings, copings, various components, joints, sealants, below-grade technologies, really anything that protects the interior of your building from the exterior environment. Like I said, a building envelope, a very important component there is roofing. However, for the focus of our session today, limited time, we're going to focus on the most common wall systems in the industry today. So the focus on the most common wall systems today will include exterior insulation and finish systems, curtain walls, masonry wall technologies, panelized wall systems, and those are going to be the four main wall systems that we're going to focus on today. So Russ, could you give us an introduction on what is an exterior insulation and finish system?
The exterior insulation and finish system, commonly called the EIFS or EIFS system, is a system that came out in the 80s. It was a lightweight, inexpensive way to imitate more expensive finishes. It was a non-load-bearing system that did not carry any superimposed vertical loads. And this photo here shows you an example of that. This material here is the EIFS system. To get it using conventional materials, you'd be using very expensive stones and similar materials. The way the system is put together, there's three basic components. There's the substrate, which is the structural backup wall, could be CMU, stud wall, concrete. Then there's a cavity or void space with insulation board installed after that. Some of the early systems had problems with drainage, so the newer systems have now incorporated drainage into that insulation layer. But this was then followed by a reinforced coating, cementitious type coating, and then a finish coat to simulate the color and texture that you were looking for.
Yep, good. Now, on this slide here, we just have a couple graphics, a couple details really showing how this EIFS, or EIFS, as Russ had said, is constructed. The image on the right-hand side really shows you from exterior to interior how this is put together. You have all your finish coats, base coats, insulating materials, reinforcing fabrics, and then your framings and backups there. The most critical part, and that's why we have it blown up on the left-hand side of this graphic, is the drainage system. As Russ said, original EIFS systems did not incorporate drainage, and that caused a lot of failures. So you want to make sure that you have a drainage tract that would allow for moisture that's penetrated that system to make its way to the exterior. A way that you could tell EIFS from concrete, as Russ said, EIFS is a relatively inexpensive way to look like a concrete wall, also provides insulating value, but a real easy way is you can take your finger or a key and go outside and actually knock on that wall. And if it's hollow and it feels very light, That's an easy way to tell that that's an EFIS system rather than a concrete system. Next, on the overviews of the exterior wall systems, we're going to look at curtain walls. And really the definition of a curtain wall is any wall of any material which carries no superimposed vertical load.
So here's a couple of examples of some curtain wall systems that have been used. The curtain walls are essentially a barrier system, so the materials that are used in them are going to be or impervious materials. A couple of typical examples would be glass or metal. Since they do function as a weather barrier, you're looking for materials that will stop moisture intrusion and prevent structure damage.
Definitely, and I think the definition clears it up, but always, maybe when I was younger, before I got into building envelope technology, you see these amazing structures. Picture the Sears or the Willis Tower in Chicago, and I was thinking to myself, how in the world can this building that's 1,000 feet tall, how can that be structurally sufficient just on windows? But having known how curtain wall technology works, it's really just a framing system that transfers the gravity and the wind loads of that curtain wall to the building frame. And this is a really helpful graphic in showing how that's all put together. You can see there's anchor systems that actually secure to the structural framing of the building. Then you would have mullion systems that would run vertically. Then you would take some sort of pre-assembled unit, as Russ said, like glass or metal, lower that into the mullion system, and then provide some sort of interior trim. But there you have a system. It's just totally framed to that building, and it's transferring all the gravity and wind loads to the actual building frame.
Here we're looking at a couple of examples of how these frame systems can be installed, and we're looking at the classic correct and incorrect. Looking at the incorrect for starts, what is going on there on the right-hand side is there's a single combined anchor point there that's supporting the upper and lower panels, and then a sealed or sealant material is placed between the two panels. Although this will obviously hold the materials in place, the difficulty with this type of system is that as soon as that sealant joint fails with time, and they will fail with time, you get leakage and there's no backup system for it. The system on the left will also provide the structural support, but it incorporates a sloped surface so that any water that comes into that can drain back out. That the left vertical leg there that shows is a gasketed connection into the upper panel, and then any moisture that comes through the panel, whether it's through a crack or whatever up above, comes down, and that right vertical leg acts as a stop for that, so it can't get to the building, and it isolates it and maintains that barrier.
Right. Now, Russ, on this slide, and I've got to ask you this, why would someone do it incorrectly, as the right-hand graphic shows?
You can see from the way these are configured, it's obviously more expensive to manufacture these types of anchorages, and they take a little bit longer to put together, so it's a more expensive, a little bit more time-consuming way to do it. And if someone's trying to minimize costs, they may go to the right-hand option, but they're going to end up with much shorter durations before they have to go in and do significant maintenance.
Okay, so kind of a cheaper upfront cost there.
These images here are just showing some examples of how some of the steel materials that are used to anchor the glass into these systems, they provide a moisture barrier, also provide a little bit of movement absorbing ability so there isn't cracking from from wind loads and so forth.
Okay. Good overview of the curtain wall systems there, just executive overview of really what that is. Next, and probably, Russ, the most common type of wall system that we see today would be masonry wall construction. And just a couple of examples, they're very, very common examples. It seems like we see these buildings all over the place. You can see on the left here would be a typical office building. On the right could be, a school, some sort of manufacturing type facility, but very, very common construction that we see all the time.
Masonry comes in a couple different, basically two primary types of construction. Mass construction and cavity walls are what people are most familiar with. Mass construction has been around since the time of the Egyptians and the Romans. The difficulty that it had was there was no reinforcement such as we have available now. So the weight of the construction required the walls to become much thicker as they became taller. Got an example here coming up of a type of mass construction. This is a two-white system, so there's two layers of brick there horizontally. Masonry that uses the mass construction type relies on the wall thickness to resist moisture intrusion. Masonry in general is a porous material, so the intent was to provide enough thickness so that the moisture could only absorb in so far before the rain event or whatever backed off and allowed it to start drying out again. The construction type that most people are familiar with now is the cavity wall system. This uses a structural backup wall, which may be concrete, maybe CMU, maybe a stud wall type system. And then a void space is provided, which may or may not be insulated. And then an exterior veneer of masonry is installed. As we're talking with the mass concrete, moisture will penetrate the masonry veneer. So the void space is provided to allow a drainage path for that moisture to drain down the inside face of the brick. And then flashing and weep systems are used to force the moisture back outside of the structure.
Okay, so now that we have an understanding of the two wall construction types in masonry, one being mass wall, two being cavity or veneer wall, let's take a look at the different material types that are used within masonry wall construction. The first material type in that first category would be brick. You would have brick masonry, which would include clay masonry, split-faced brick, ceramic glazed brick, terracotta. And one thing that we'll get to that you must note when dealing with brick masonry construction is that there's different weathering grades. And I've got a map here that we're going to get to in a while that shows the different weathering regions for each brick type. The second material type would be stone. You could have granite, limestone, sandstone, slate, marble. These could be laid in mortar, could be mechanically attached, a number of different ways to do that. Third would be your concrete masonry unit. So you could have, again, concrete masonry unit, split-face concrete masonry units, concrete blocks. Nice thing here is there's extensive sizes, extensive varieties. As we're going to see here, we've got good examples of masonry construction incorporating a number of different material types. You can see there's different types of brick and stone here on the left. On the right, we've got brick combined with, there's some concrete masonry in there, and then also a concrete base there on that building. So just a number of different types within masonry construction. Two things on this slide that we want to focus on. We'll start on the left, and this is dealing with the mortar joint profiles. This is, if we're issuing a test, this would be a test question, but looking at the different joint profiles, extruded would be the least effective and they would gradually improve as you go up. So the joint profile that you're really looking for is a concave mortar joint. You really want to make sure it's well tooled. When a joint is tooled properly, it compresses the mortar, making it more dense, more resistant to moisture penetration, gives a better bond to the masonry, and is really a more effective joint. Next, on the right-hand side, I spoke about the concrete construction. We have a split-face concrete block here, very, very common in commercial construction. I mean, if you've seen like a lot of retail stores would have this. One of the major downfalls here is it's very, very moisture absorbent. So you need to make sure it's coated. And you can see that on the left-hand side of the photo. You can see that it's coated, and it actually has that wetting action. You need to coat it to support with that moisture resistance. But it's very, very important, and Russ is going to talk about this in a little bit, to make sure that you don't suffocate the wall system with improper coatings. So good executive summary of masonry wall systems. Next, we're going to look at the fourth major wall system, and that is a panelized wall system.
Panelized wall systems come in a lot of different types. The primary purpose of a panelized system is to allow large areas to be installed as a single unit. So panelized systems may be metal panels, it may be precast concrete panels, or they could be stone, masonry, brick, or similar materials that are all pre-assembled into a panel and shipped to the site. We've got a couple of examples here. The building to the left utilizes a metal panel wall system. The one in the center there is a precast concrete system, and the one on the right there is a pre-assembled brick unit system, and you can see that one actually being lifted up into place as one unit. Some of the advantages of that also is that it allows some very architectural systems to be installed for a less expensive price because they can be done in a factory-type environment. The photo you're seeing here is some examples of insulated metal panel wall systems. You see there's a tongue and groove type system there that provides a weather lock between the panels to minimize moisture intrusion. A simpler type system here is just the single ply metal panel over a light gauge metal girt system. The metal panel obviously is impermeable itself, but it still requires that proper drainage and flashing at the bottom be provided. You can see that in the left photo, to make sure that any moisture that gets in, whether it's from condensation or water sources that are beyond the control of the wall, coming from the roof or wherever, make sure any of that moisture can drain out of the system, not become trapped. A couple of examples of precast concrete wall systems. A lot of different styles and shapes can be provided with these, different surface textures, but the only thing that limits them is the size that can be transported on a truck on the highway. Here we're looking at how these panels are installed. This one is actually looking at a thin stone panel system, but it's the same general idea for all of these. We're looking at the bottom, there's a rigid anchor connection that provides resistance to gravity loads and wind loads. And the upper connection is a more flexible type of anchor that stabilizes the top of the panel, helps stabilize the bottom of the one above it, but mostly it allows for flexural movement as the panels swell or shrink with temperature and wind loading. Here we're looking at top picture, obviously, is installing one of these panelized systems into a structure. The detail showing right below that, a couple things we wanted to highlight. This is a hidden connection that you'd use for an architectural panel. Obviously, if you're putting the money into a nice panel system, you don't want a lot of connections showing. But to make sure they continue to be non-visible in the future, there's some things you have to include. The anchors need to be a non-corrosive type material, so we're looking at galvanized or even better stainless steel anchors. Using plastic shims and washers to isolate any dissimilar materials so you don't get a dielectric corrosion effect there. And then cushioning strips in the anchor bedding area to smooth out any high spots or irregularities.
Good. Yeah, good. Really good overview, Russ. So that is an overview of the 4 most common wall systems in the marketplace. So again, exterior insulation and finish systems, curtain wall systems, masonry systems, and panelized systems. So now we're going to move on to what we're calling subsystems or common components found within each system. So one has to be openings. We're looking at windows, doors, grills, louvers, penetrations found within these wall systems. Just looking at some examples here of the grills, louvers, flashings, just a number of components that are common within each wall system that we discussed. Now, I know this is something that Russ can attest to, but when we're going out doing evaluations for clients, one of the most common problems that we see with wall penetrations in openings is specifically with penetrations like we're seeing now, maybe ductwork or electrical coming through the wall. It's not sealed properly. If these things aren't sealed properly, that sealant is failing or it's open, that's a direct avenue for moisture ingress into the facility. So you just want to make sure that if you have penetrations through the wall system, you are making sure they're sealed properly and continuing at the maintenance, because if not, it's just a direct avenue for moisture into the system. Now, one thing on joints I want to hit on here. Joints is very common in all the types of construction we talked about, but Russ, with these joints, we have 3 listed. We have control, expansion, and isolation. All the time, I hear these used interchangeably. What's the difference?
In some ways, they are all they're all joints. So essentially, what they are is a means of providing a location that can be sealed and forcing the building to either crack that location or to address a separation that's already been provided there. The primary differences between them is what their intent is. Control joints accommodate the growth or the shrinkage of individual component materials. Masonry units typically grow over time. They absorb moisture just because of the way they're manufactured. You know, the moisture is all baked right out of them. So over time, they are going to gradually absorb moisture and they grow. Concrete, conversely, as it continues to cure over time, shrinks. So you can get either way, you're accommodating either the growth of and you're trying to keep them from smashing against each other, or you're trying to allow for them to shrink and separate and still have a good seal at that location. Isolation joints provide a seal between 2 dissimilar wall construction types. Here's an example of a control joint. So it's accommodating the long-term shrinkage of these concrete masonry units. One thing you can see is at the top there is no joint that's forced into that coping. So that's one way to tell that it's not an expansion joint. One other thing that needs to be considered in these wall systems is the type of reinforcement that's used. The truss type reinforcement that you see on the left there is a very rigid type of material. Does not do a real good job of allowing movement that you get from the 2 sides of the wall being exposed to different temperatures. The latter type, when you see to the right, is a little bit more flexible and accommodates that type of movement. these two photos really highlight all three of the types that we were talking about earlier. To the far left, you can see the vertical control joint that's provided for the masonry. And then there's a horizontal joint at the lintel right above the top of this window system. That's providing isolation between the masonry and the framing. And the photo to the right is showing an expansion joint that's allowing movement between the two different sections of the building itself. A couple more examples here. This is isolation joints. This is the photo to the left. That black-looking section right there is actually a steel column, and isolation joints would be provided on each side of that between the column and the CMU. The other example shown there is a stud wall matching up to a brick wall. You still need to make sure that connection between the 2 points is sealed.
Yeah, Russ, and that's a great point. I think one of the things that shows the critical importance of these isolation joints, and a lot of the people that are on today, managing hospitals, manufacturing facilities, schools even, that they've got an original 1920s building, and that was the original section of the plant. Now they came in, they have a 1950s addition to that plant. They've got a 1970s addition to that plant, 2000s addition, and they're all using different materials, different construction procedures, and it's very critical to make sure that these buildings are isolated from each other.
Correct.
So this next slide, and before we get into this, Russ, this is something we might want to address here, this picture on the left. I wish we would have caught it, but Russ is a key member of our safety team here at Structure Tech, so I have to ask him, is this gentleman, is he safe? Do you think that's an OSHA-approved deal there?
Well, Mr. OSHA there definitely does not meet the OSHA criteria. He's not wearing a hard hat for the most obvious one. But you can't tell very well from that picture, but he is up on a scaffolding system, and there's no tie-off for him or any of that type of stuff. So, but what he is doing up there is providing caulk seal where those two different wall sections come together. One is an original masonry, and to the left there is actually a clad frame system of precast materials. And then to the right, what we're showing there is that you can see the backer rod material coming out of an isolation joint. Proper materials used as the backers for these is important to make sure that you get the correct depth and profile of the sealants. And you're looking for a 1-to-2 ratio of the depth to width on these, and a 2-point adhesion for the sealant to get proper movement out of the seal.
Okay. Good. Now looking at something very critical, Russ, in this next building wall subsystem or building wall component would be flashings, looking at through-wall counter flashings and weeps, sill and head flashings at the wall openings. One of the big things here that we see, especially with weeps and flashings, is you need to make sure that they are clean, that they are not clogged with mortar or something like that. Just if you've got a flashing that's capturing water and your weeps are plugged, the moisture is not going to get out of that facility. So it's just critical to make sure that they're kept free of any debris. And we'll look at a couple of examples here.
These two details show cross-section through the cavity wall at an anchor or at a lintel or shelf angle. And on the left, you can see there's a steel angle anchored into the backup wall. And then coming down from above, you can see a line that swoops down over that anchorage and then turns and goes out through that wall. That is the flashing that we're talking about, that carries any moisture that's inside that cavity down and then out through a weep system. On the right-hand side, you can see a similar situation. That kind of crosshatch section there that shows there is an insulation board. It's important to make sure that your flashing still accommodates and is continuous to prevent water from backing up through that detail.
In Russ, it seems like more and more now we're running into buildings that are 10, 12, 7 years old even, that they have failing flashings, PVC, rubber, mod bit, and these flashings are failing what would seem to be prematurely. What would be the ideal material to use for a through-wall flashing?
Well, as you said, there's a lot of materials have been used in the past, anything from bitumen-type materials to tar papers to plastic sheeting. But what really works best are the materials that we know have long life to them, which typically is going to be the non-corrosive type metals. A backup flexible membrane over the top of them is always still a good idea, but the base flashing would be typically a stainless steel or a copper flashing.
Okay.
At the top of a wall is actually another place. The coping, sloped coping you see up there at the top can really be thought of as another through-wall flashing. When you look at how masonry is constructed, there's a lot of vertical stacks of brick, quite often with void spaces between them or mortar, and that leaves them very susceptible to moisture intrusion. So it's critical to get a dependable, long-lasting water seal over the top, and that's what that coping flashing does for you there.
Okay. Okay, next we're just going to look at some examples. Like I said, the flashing systems. We're looking here at how some of the penetrations have been flashed, or the openings have been flashed. Specifically, we're looking at the importance of end dams on that right-hand picture. You want to make sure that the flashing is terminated properly, or else water will continue to travel horizontally, never get captured and sent out of the system. If it's not end dammed properly, the moisture will find its way into the interior of the facility.
When you're looking at building wall water protection, one area that quite often gets overlooked is what happens when you get down to grade. The weatherproofing system above grade, typically is sealers, coatings, damp proofings. There may be integral water repellents cast into CMU materials, that type of thing. But once you get down to the grade level, there's a high potential for standing water against that wall system. So that has to be a true waterproofing system, not just weatherproofing. A couple of examples here. Water has gotten into the subgrade below a plaza system, caused damage to the plaza surface, but what isn't always recognized is what that water can also do to the structure down below, which you see to the right. It's caused damage to the basement wall system in that area. An example of some of the considerations when you're looking at below-grade waterproofing, as a plaza deck really can be considered similar to a roof. You have occupied space below this area that has a high potential for standing water. So any place we have a horizontal to vertical transition needs to have multiple layers of protection. You can see at the corner point there's a fillet type joint system in there, and then there's a wider flashing that extends up and horizontally, and then finally the large area waterproofing comes up to it and extends vertically up to a counter flashing. The overburden material that's in there can be a lot of different things, but it has to include a drainage system to a functioning drain outlet. As an example here of a vertical wall system, we still have the same considerations. We have to provide that protection at the horizontal to vertical intersection. An example of a material that's quite often used in cast-in-place concrete where there's a cold joint. This is a rubber-type material. It's got a center flexible piece there, and the two wings that embed into the concrete on each side. This provides a barrier that's built right into the wall at that joint condition. There's a couple examples of some weather protection that can be provided on the building wall subsystems. you can see in the left picture there's a darker area there, and on the left it's a lighter color. And what this is waterproofing has been provided. It's a clear system. It may actually darken the mortar and the brick a little bit initially, but when you look closer at the right-hand side there, you can see the right-hand side, this area has been sprayed with water. The right-hand side has soaked in water, and on the left-hand side, it's a little hard to see, but there's beads of water standing on the surface.
Okay. And that's a really good overview. Now, looking at, we've discussed the common types of wall systems. We've looked into the most common components. Now we're really going to give an overview of identifying problems and really what goes into that. We always need to start by introducing this construction pie. Really, 3 parts for a successful project are design, materials, workmanship. A way I always like to discuss this is like a 3-legged stool. If any one of these legs is missing, that stool is going to fall right over. You could have great design, fantastic, best in the industry materials, but if that workmanship is not what it should be, that's going to be a failed project. Same would go for great design, awesome workmanship, ineffective materials, it's going to be a failure. So you need to identify problems and look at these 3 key areas that need to be there for a successful project. Just looking at first design, we need to design around these 5 different principles that move water. 1 is gravity, 2 would be surface tension, 3 would be air pressure differences, 4 would be momentum, and 5 would be capillary action. And these are really the 5 forces that you need to design around because these 5 forces move water. Next is, Russ said, proper joint design. You need to incorporate in your designs proper joint design. The one thing that I want to focus on here, a couple things I want to focus on here. 1 is on the left-hand side, we have proper width to depth ratio. 2 width, 1 depth. Next would be you have that backer rod, which provides for the right amount of adhesion and just allows for that nice tooled concave joint. On that pour design there, major thing is it's too thick. It doesn't have the right geometry. That joint is going to work against itself because it can't move properly. And then this here is just really hitting on a moving corner joint. You can see on the left-hand side there is bond breaker tape that was incorporated into that design, which allows for 2-sided adhesion, which is going to allow that joint to move, be flexible. On the right-hand side, we have the pour joint design, no bond breaker tape installed there. We're going to have 3-point adhesion. That joint's going to work against itself, and it's going to fail prematurely, no question about it. I talked in the introduction about the different weathering grades of brick. Here we have the map. We can see in the Midwest, East Coast, we have what is called the severe weathering grade of brick. In the central region, we have a moderate weathering grade. Far south, talking Texas, South Florida, Southern California, you have a negligible weathering grade. Very, very important that you don't use the wrong grade of brick in the wrong climate. Here we have a brick that was fired for southern use. It was installed in the north. It hasn't really taken effect yet, but that southern grade brick is going to be far too moisture absorbent, going to take in too much water, not going to be able to withstand the freeze-thaw cycles in this northern climate. And that is a major problem that you really need to be aware of.
A couple of examples of some test openings in some wall systems. The upper left is showing what happens with the materials that are not durable. We got some cracked flashing showing there and heavy corrosion of the steel angle. On the upper right, you can see splits in the membrane flashing. And down at the bottom is the type of system we would recommend for proper flashing over this type of condition. You've got a continuous stainless steel metal flashing that comes as a vertical leg up the wall, comes down, laps over, and turns down, and then has a secondary membrane flashing over top of that.
Good. Next here, this is dealing with, we've got a through-wall embedded flashing that's coming out of the wall system. Great design, great design. Problem is we have poor workmanship, poor execution. That was covered with mortar, and which allowed it made the flashing ineffective. It trapped the water inside the system. Good design, poor workmanship.
This is an example of good design that wasn't carried far enough. If you look close, you can see that there was proper flashing in there, but there was no end dam condition, which led to failure of the brick.
Now looking at identifying problems, what are these consequences of deferred maintenance or consequences of neglect? Well, one, and this is what you feel the most, it's water or moisture intrusion, it's leaks, it's what you get the calls on, that's what you're getting complaints about, and that's what's causing everyone the headaches. But really, on top of that, you have damage to the insulation, interior finishes, equipment, general deterioration of the facility, and even structural distress. Now, just looking at some examples here, consequences of neglect. These walls have been neglected, and when they went to make the repair, just so happens that they used the wrong materials. They used an asphalt roofing material or roofing cement to seal the cracks, suffocated the wall, created more harm than good, not effective. This here, I want to just touch on this real quick. This left-hand side, we're looking at the interior of a facility, but we see that white, chalky substance on the interior of that wall system, and that's efflorescence staining. Doesn't fail. I get questions on this all the time. But Russ, what is efflorescence staining, and what's the cause of that?
Efflorescence is caused when moisture over a long time is moving through the wall, and it's carrying dissolving and carrying some of the calcium materials dissolved in the water. And then as they dry, they deposit it as calcium carbonate or calcium sulfates. This is similar to the process that you see in caves where stalactites and stalagmites are formed.
Okay. So that's indicative of moisture in the wall system.
Long-term continuing moisture.
Okay. What is this?
When you're looking for problems, you're going to be looking for identifying symptoms typically, and they can range from relatively minor conditions, surface corrosion showing here on the steel lintel over these windows, to more significant, more severe conditions that are actually affecting structural elements. Moisture is a very aggressive material. These concrete sections here, in this case, the reinforcing steel was placed too close to the surface, so when the moisture absorbed into it a little ways, it was able to start a corrosion effect there, which broke the surface concrete off, and it will continue to get worse the longer it's exposed. A couple of examples of movement-related. On the right-hand picture, you can see there's a diagonal crack there. That's called stair-step cracking, and that's typically indicative of movement of that wall trying to flex and the masonry resisting it. And the left-hand picture, that large vertical crack there you see, generally indicates thermal expansion of a wall, but the corners being restrained by a stiff column element. And here we got just a couple examples of deteriorated mortar exposing the edges of the brick.
And so this one here I want to touch on. I said make sure when you're applying coatings, sealants, sealers, you're not suffocating the wall system. This is an example here. Leakage in a facility. The executives were getting impatient with the facility manager. So finally the facility manager says, hey, maintenance staff, why don't you run up to the Home Depot or the local Lowe's, pick up some waterproofing sealer, and we need to get these walls waterproof. So sends them out. They come back with Thompson's deck sealer, similar to what you might apply on your deck near your pool or coming off the back of your house. And they applied to the wall system, suffocated the wall system, didn't allow that wall to breathe, trapped all the moisture in there, created more harm than good. It created significant problems, and that's just an unfortunate consequence there. Required full restoration of that building to correct these issues. And then what can be sometimes scary and definitely a consequence of neglect is potential areas for structural distress, structural concerns. I mean, I think the primary focus is keeping your building occupants, keeping your visitors, and anyone around safe. And if you're looking at structural concerns due to moisture ingress in the building and long-term neglect, that can be pretty scary. So you definitely need to look at these types of issues, make sure that you're being safe with your facilities. Now, just in closing here, another 3 minutes of presentation, and then we'll be moving on to the question and answer, but problem solving. You need to do the thorough investigations. Our buildings are talking to us. We need to make sure that we're listening. You need to look at visual observations, exploratory, either destructive or non-destructive testing, leakage testing, and monitoring equipment. And we'll just look at a couple examples here. This is visual investigation, actually getting up close and personal with this metal panel building. You can see the swing stage. You've got the engineers. They're taking a real hard look at what's causing the failure in this example of that metal panel, really finding out what's going on.
Here's a couple of examples of exploratory excavations. On the left, you can see that the flashing was done very nicely. They got it all wrapped in, but they didn't carry it quite far enough. On the right, you can see that there was a flashing installed, but it wasn't secured down, so there's a moisture path back underneath the flashing.
I mean that shows the importance of those exploratory openings. From the exterior, you can only see what you can see. If you never got into that wall, there'd be a whole lot of unknowns.
Here's an example of testing on the concrete. There's a non-destructive type. It's a method for measuring the depth of the embedded reinforcing steel to determine how susceptible it is to ongoing corrosion.
Okay. In this here, this is a great example of two things. One on the left, that gentleman there is performing water testing. And really what you're doing when performing water testing, you're trying to recreate leakage conditions. So there's some real high-end hosing and rack tools that you use that could really recreate different rain events, driving rains, drizzling rains, whatever you want. And you can isolate various details in the wall system and the roof system to really recreate these rain conditions and find out exactly how that water's getting in there. Very, very effective testing. On the right, that's a rhyolum tube. What you're doing there is filling that tube with water, and you're monitoring the rate of absorption through the masonry and the mortar joints. It really tells you how porous these bricks really are. And then next, designing solutions. We've identified the problems through our visual investigations, our exploratory work. Whatever testing we did, we identified those solutions. Now we've got to put designs that are going to remediate the cause of the problems, not just the symptoms. So looking at sealants, coatings, waterproofings, flashings, reconstruction, what's the right option, and let's design around that. So it's looking at various design considerations, making sure that you're doing the proper things, sealant configurations, fixing existing masonry cracks correctly, incorporating expansion and control joints into the existing masonry system to allow for that movement, as Russ had said. And then really just This is a prime example of making sure that you're going after the cause of the problem, the underlying cause, not the effect. You want to treat the disease, not the symptoms. This here, I'll keep this story brief, but school district, significant leakage. 2 years in a row, they went out to bid with a local contracting community. They had an architect specify tuck pointing of the facility. After year one, they were still having leakage. After year two, still having leakage. And they did a full tuck pointing of that building. Eventually, we got involved in the facility. We did some more exploratory work. We found out that the through-wall flashing system was in very, very rough shape. There were severely corroded lintels, a lot of underlying issues that was never addressed. They had to fully replace some lintels, redo that through-wall flashing system, redo the tuck pointing yet again, but that's spending good money after bad. They spent a whole lot of money on that tuck pointing 2 years in a row, but they never addressed that cause, the cause of the problems. So what do you know? They still had those symptoms. So you want to treat the cause of the problem, not only the symptoms. And then project management in closing, we want to drive some of these points home. In project management, you need to review the alternative design solutions. There might be 3, 4, 5 different options in design, but once you have those options, you want to review the pros and cons, see what fits within your budget, perform the right life cycle cost analysis. You want to see first cost of ownership versus life cycle cost of ownership to determine what that best solution is for you. And then a very, very important point is service life engineering. I gave an example 30 minutes ago about new buildings, 7 years old, 10 years old, 15 years old. We're going in, and they have flashings, through-wall flashings in these masonry buildings that are failing. That's unacceptable at 10 years, and it's due to ineffective materials, improper materials. Why on earth, if you're looking at staying in a building for 50 years, would you put a material in there that has a service life of 10 to 12 years? That doesn't make any sense. You need to look at service life engineering, see the overall goals and objectives for this building, in design around that service life to ensure that what you're doing is going to meet your overall goals and objectives. And that's just a really, really important point that I want everyone to take away from here.
So the design approach and life cycle cost analysis is a balancing act. It's trying to find what's going to be the maximum return on your investment, what's going to be looking at the length of time that you expect to keep the building. Is it one that's going to be demolished in 5 years? Is it one you're going to keep for the next 100 years? We're going to compare that to the cost, but also to how frequently you can tolerate the inconvenience of restoration. So the balancing act between the three works together, and what you'll be looking at is deterioration progresses no matter what. And so what you're looking at is at what point in time does the cost and the life of the structure and the frequency of interruption work out for you to do the repairs to bring it back as close to original construction before you let it go and let the deterioration do its normal thing again.
If you're making the proper investments at the proper time, you can really manage the overall life cycle cost of that building.
Right.
Good stuff. Well, great presentation. I think we covered a lot of information in a short time period for sure. But we do have some questions here that we definitely want to hit on. I think we can we'll get a few in. If we can't get to them all, we will follow up under separate cover. But Russ, we have Scott from the Atlanta area, and he's asking for further clarification on efflorescent staining. What Scott's saying is that he has a building that has the white efflorescent staining on the exterior, but no signs of moisture intrusion on the interior.
Basically what that tells you is that moisture is getting into the wall system, but it's finding a easier path to escape through the outer surface than into the building at this point. At some point, if it finds an easier way to leak into the structure, you'll have moisture coming in.
Okay. Let's see here. Here's a good one. Okay, we have Randy from Minnesota. Randy's wondering, I have stair-step cracking in a few different areas in my facility. Is that a sign of structural problems?
It's a sign of structural movement, which may or may not be a problem. What's important is to make sure that that movement is being accommodated properly by joints and systems.
Okay, so not necessarily a structural failure at this point? Or?
Right, it's not a structural failure. If you don't provide a joint, the building will make its own.
Okay. Thanks, Russ. Let's see here. Good question. Okay. So we've got Jim from the Chicago area. Jim's asking, do all weathering grade bricks absorb moisture?
All bricks absorb moisture. Weathering grade bricks absorb less moisture and are less susceptible to deterioration.
Okay. So in the northern climate, your severe weathering grade brick is still going to absorb moisture, just less moisture resistant than the ones that would be used, are more moisture resistant than the ones that would be used in the south.
That's correct.
Okay. Good question for me that I know I can answer here. So you discussed on the start of the presentation, EIFS looks like concrete. How, again, can we tell the difference between EIFS and concrete? I think the easiest way, at least the easiest way that I found, is going outside to the exterior, taking your key out of your pocket and just giving it a couple quick taps. You'll notice it's hollow, and you'll be able to tell. If it's solid, it's concrete. If it's hollow, sounds kind of like a drum. That's EIFS. We've got time for one final question. This is a good question. Russ, how often do masonry buildings require expansion joints?
True expansion joints for accommodating building movement typically shouldn't exceed about 200 feet in spacing. Control joints generally are down more in the 20 to 30 foot spacing range.
Okay. We've got a lot of questions here yet that we unfortunately are unable to get to. However, we'll make sure to follow up under separate cover. But I can't tell you how much we appreciate your time this afternoon, taking an hour out of your day to all come together and really learn about building envelope restoration. So any questions, please don't hesitate to reach out to us, and we would be more than happy to support with any question that you had. Also, just a listing here of upcoming events, different venues where we'll be presenting. In February, we have a building envelope forum that we're putting on in Ann Arbor, Michigan. In March, we will be attending the NFM&T conference in Baltimore, Maryland. If you're there, stop by our booth. Also, we'll be giving a presentation at that NFM&T conference March 4th at 10 a.m. on roof restoration. And finally, we'll be down in Atlanta in March for another forum. So we appreciate everyone and have a great day. Thank you so much.